Thanks, I've really enjoyed being here. And as she said, I'll be talking about the role of spatial thinking in STEM, and just to make sure we're on this, since this is an international conference, STEM stands for Science, Technology, Engineering, and Mathematics. It's a major focus, at least in the United States, because we don't have enough STEM workers for the future. And I will be making the claim that spatial cognition could be both a limiting and if we do it right, a contributing factor to solving the problem. So the first thing to discuss is there is a strong correlation between one's psychometrically assessed spatial ability and STEM attainment. Attainment means not just what grades you get, but whether you actually go into STEM careers. This is based on a study that Wei, Levinsko, and Benbow did of where people who were first assessed in 1960, and they're still going back to their high school reunions and such, they're in their mid-50s now, they are looking where they ended up. And these numbers, like the 23 and 87, represent the number of people out of a sample of about 100,000 that ended up in these STEM careers. So it's not a lot, and maybe that's an illustration of the problem. But what this graph is really about is the relation between spatial ability and going into one of these STEM fields. And you can think of the arrows as a vector or third dimension that shows the relative contribution of spatial ability to predicting who would go into the STEM fields, like science and math. And the thing you notice right away is that for science, mathematics, and engineering, spatial ability makes a very strong contribution. In fact, in some cases, it's stronger than math or verbal. For example, in the sciences, the math advantage is very small, about 0.1 standard deviation. There's a verbal advantage, but the science advantage is about the same as the verbal advantage. And for engineering, the spatial contribution is extremely high. And as we'll see, it's about 1.5 standard deviations in the population as a whole. Okay. So there is a strong correlation. And by the way, more recent work has come out that spatial ability also predicts creativity as defined by patents instead of just publications. So it's important for both attainment and for creativity. But the question is why? And there's a putative assumption that I'm going to address that I think is not the answer. And I would propose another answer that has to do with the beginning. Okay. So my theory is what I call spatial ability as gatekeeper to STEM, and that spatial ability contributes to STEM dropout. Specifically, some students start taking STEM, it's very spatially intensive at the beginning, and they drop out. However, the good news is, with time, if they could stay in, it actually becomes less spatially demanding. So true experts don't sit around mentally rotating figures all the time. That's quite intensive, and they use a lot of semantic knowledge instead. Spatial knowledge can complement that or spatial skill, but a sort of a characteristic of learning in these fields is a shift from general ability. This is well documented by Ackerman in many different fields, that general intellectual abilities become less predictive with time, and spatial ability is an important case of that. Also, a new part here is I'll be talking about the role of STEM joining, of spatial skill in STEM joining. STEM joining is the opposite of STEM dropout. It is coming into STEM from other fields. It's barely been addressed at all, but is a very important way of addressing this problem that we've barely touched. Okay, and then the second half is what can we do to help, and I'll give two specific suggestions. Okay, so here's the putative or common explanation. Most people, when I say there's a correlation between spatial ability and STEM, will say, oh yeah, a geologist or a chemist has to be able to think spatially, and of course the experts who are really, really good will have really, really high spatial ability. Here's an example, a structural geologist. We have several in our center. It's amazing to watch them work, but they would have to figure out the forces that led to these falls. Organic chemistry is notoriously spatially demanding in the beginning. And so I'm fond of saying it's the greatest source of psychology majors. And I think part of the reason for that is the spatial demandingness of it. Okay, so that's the common explanation. These are highly spatially demanding, and therefore you need high spatial ability. End of story. There's nothing to explain. But it actually gets a little bit more complicated than that. As I suggested, spatial ability tends not to predict expert performance. The further you go in STEM, the less predictive spatial ability becomes. And I'll go through a variety of domains where, whenever this has been studied that I can document, they found the same pattern. Now, this is just sort of a survey of literature at this point, but the pattern is quite strong. Geoscience is the best documented. After I go through those, I will also, to help sort of shed light on wild, consider foils between chess, which follows the exact same pattern as the STEM sciences. As you go further up, spatial ability becomes less important. The one exception to that is Scrabble, a Scrabble skill. Scrabble is an American, well, does everyone know what Scrabble is? It's a game where you form letters on a board. I have a picture later. But their spatial ability remains predictive all the way up to the highest level of expertise. And that foil, if you will, helps us to localize the cause. Okay, so this is the study of geoscience and the role of spatial skills. I'm very fond of this study because it really measured geoscience performance in the field, literally and figuratively. Zach Hambrick and his colleagues took first year, that is after their freshman year, students from Michigan Tech and advanced graduate students out from Michigan to Montana to do an authentic set of geological tasks. And in addition, they measured several psychometric properties. And one of the tasks, a very common task that a geologist has to do, is based on observations on the surface, determine the forces and the structures underneath the earth that might have led to that observation. So geological mapping involves not only mapping on the surface, but some inference or induction about what might be under the surface. And he measured the relation between the ability to do that and spatial skills in experts and in novices. The map accuracy score is a sort of a cumulative, summative measure of performance on that task. I don't know why I keep doing that. I'm giving away all my, okay. Stay, even though the surprise is blown, please still stay. So what this is showing us is that for the experts, spatial ability doesn't predict performance at all. In fact, the low spatial skills are spatial experts are even slightly better. But there's a huge effect of spatial ability in the non-experts, the novices. And this is a pattern we observe over and over again, that spatial ability becomes less important as you move through the ladder of expertise. And importantly, it is not just restriction of range, which is a very good thing you might ask here. Maybe there are no low spatial geologists, but when you look at the standard deviations for the different groups, they're almost identical. And so there was the possibility of finding covariance, and they did in some cases and didn't in some other cases, and that pattern is quite revealing. Okay. I'm so low spatial I can't figure out which is forward and which is, okay. Okay, I don't think that's going to happen. Okay. Another example comes from the domain of chemistry, and this is from Mike Steiff's dissertation, which, by the way, included not only these psychometric measures, but also an intensive qualitative analysis of problem solving. So across the 462-page dissertation, I was on his committee, and so I painfully know how long it was, but it was all worthwhile because it revealed a great deal about the role of spatial ability and expertise in chemistry. And amongst the many tasks he did was a comparison of mental rotation of the classic abstract Shepard and Metzler blocks, as well as different chemistry projections. Does everybody understand the task? Here is just like a regular mental rotation task. But here, the materials that you're asked to rotate are chemical representations, and now we have the possibility of semantic knowledge coming in. These are deliberately designed to have no real semantic knowledge. Maybe over the last 40 years, there have become some experts on three-dimensional abstract blocks, but for the most part, it doesn't help. But here, if you knew something about the properties and the spatial properties and whether they can be rotated or not to be the same position is a fundamental fact in a lot of structural organic chemistry. So that's a major semantic fact that will often reduce the time needed to mentally rotate or eliminate the need to mentally rotate. So, so this is the standard correlation between the degree of rotation and reaction time. Everybody's familiar with this. And let me just say, in some of the chemistry stimuli, Steve found a flat and low line. The experts are very fast, and there's no discrepancy, there's no correlation between rotation and reaction time. And the reason is because they're using a fundamentally different process, and this is confirmed somewhat in his qualitative analyses. They just know. That's a chiral molecule. Yes, it can be rotated. No, it can't. And that semantic knowledge allows them to make the answer that they need to do without having to go through the rotation process. So here we get a little bit more specific about why spatial ability might become less predictive with time. Okay. Now the chess and Scrabble example, neither are STEM skills, I admit that, but they do help to highlight the pattern. So that STEM expertise is more like chess expertise. Chess really was the prototypical example of expertise. The studies go back into the 60s. Really one of the foundation studies of cognitive psychology, that you could actually kind of figure out what was going inside of their head. And there have been more recent studies that looked at the prediction of skill in chess at different levels of expertise. And lo and behold, we find the same pattern, that for novices it's very important, and for experts it's not. However, Y and Halpern showed, at least for their sample of Scrabble experts, spatial ability remains really important all the way up. And if we think about why, it helps to highlight the role of semantic knowledge and spatial skill. Okay, so for many years we believed that the chess experts, what they were doing was sort of mentally matching a prototype, so they had memorized many different patterns. But that doesn't really account for how they represent many of the chess positions. So it's part of a narrative of attack and defense. And has anybody seen the movie Searching for Bobby Fischer? Okay, and one of the things they're doing in that chess club in New York, and they're all they're wearing threadbare shirts because they're so consumed with the passion of chess, they don't take showers, they don't do anything else. But what they do, they don't play chess games all the time. They read about old games, and what they're doing is learning about possible patterns of attack and defense that can come up. So it's not at an expert level simply thinking about where pieces could be. It's much more semantically based than that. And in addition, you know the famous study by Chase and Simon, where they had expert and novices copy meaningful and non-meaningful chessboards. Okay, that is one of the things that's been used for this example of the template. Stop doing that. Okay. But when we look at a different task, we see more of the evidence of the conceptual factors. So this is even easier than just copying a chessboard. These were same or different judgments. If it was part of the same beginning game, mid game, or end game, experts would sometimes say same for boards that differed in 3 pieces. So it's clearly represented not as a particular template, but rather as a pattern of attack or defense. And this, to me, is what part of what is happening as you become an expert is not just memorizing more spatial patterns, but linking those spatial patterns to well-known historical outcomes. So they're actually thinking about prior games as they are playing these advanced games. The novice, in contrast, it's very spatially demanding. They don't have that semantic knowledge, and therefore spatial ability predicts. But now look at Scrabble. Here is the Scrabble board, and what you are given is a set of letters, and then you make a word, and you get a certain number of points for that word, and then your opponent tries to make a word that crosses some of those letters, and it goes on and on and on. Now, semantic knowledge of words is incredibly important in Scrabble, but there's still a very important spatial ability. When the experts were interviewed, they said that they could count on their opponents knowing about 70,000 words, which is roughly 3 or 3.5 times the average speaker of English. It's a lot of memorization of words. Nevertheless, there is still a real-time spatial demand in that these things emerge all over the board, and you can never tell how they're going to come up. It depends on what your opponent does. And they don't study old Scrabble games because they're not useful. So spatial ability continues to predict. So now we have some scoping of when spatial ability matters. It matters at the beginning when you are forced to deal with a lot of new stimuli that are spatially arranged, but arguably part of learning is to get you away from the reliance on spatial ability. And if this hypothesis, the spatial gateway hypothesis, is correct, it's a quite optimistic perspective because it means we could do something early on and perhaps get rid of some of the dropout. Okay. So, I just answered my question. Spatial ability matters a great deal at the beginning. As you learn the knowledge of your field, you can avoid spatial transformations. They're not fun to do. You know, mental rotation is hard, even for people who are really good at it. And as we saw, it is time-consuming. So it's better to just know the answer. Also, it becomes, another thing that reduces the role of spatial ability is you use external tools such as representations on the computer. I happen to have the opportunity to observe a lab meeting for parts of several lab meetings of 2 organic chemists, and they're trying to find where certain enzymes could bind and ultimately design a new drug. And it's a little bit of it's spatial, but as they're going through their knowledge, they're a lot of it is recalling previous manuscripts. Oh yeah, Smith tried that like 5 years ago and it didn't work. Then they spin it around on the computer. Then they'll do a little bit of visualization. Then they'll go through a list of possible molecules that they know could not fit there. So the semantic knowledge becomes incredibly important, and spatial knowledge relatively, although not completely, unimportant. Spatial ability could matter not only because it's directly required, but also, and I think as or more important, because it affects your ability to interpret the many different representations. If you look at an introductory organic chemistry class, they are overwhelmed sometimes with many, many different projections that have developed over the last 100 years or so of 3-dimensional space. And quite a few students say, I just couldn't keep up with what he was doing, or sometimes she. Not enough she, but getting better. And so the student drops out, and dropout happens pretty quickly. Okay, now here's my one way of testing that, and we're looking at many different ways. Thus far, it's largely a theoretical or sort of historical analysis. But if we go back to the Project Talent data, the same data set that Lubinsky and colleagues used, there is one way to look at this. This is, again, an enormous data set covering, this is my graduate student or collaborator, David Miller, who did this analysis. These are Project Talent sites all over the country. And as I said, to the extent that they can find them, they've been followed for years. And one of the things that makes Project Talent so wonderful is that largely by pure luck, they decided to include 2 spatial abilities measures. Spatial ability is relatively ignored, and in this case, it wasn't. And those 2 measures have turned out to be extremely valuable for learning. Okay. So I'm going to show you a graph that shows the relationship between spatial composite score, which is a sort of where you stand relevant to others. So 0 would be your average, and your probability of persisting in STEM. So this is given that you identified as a STEM person, somebody who wanted to be a STEM major. Did you stay in STEM? There's 2 plots. Okay. So the bottom line with a steeper slope is from high school to college. And this is consistent with the spatial gateway hypothesis. These are people who identified as wanting to be STEM majors in high school. And it shows that spatial ability became more and more predictive the longer they stayed in. The reason is because they're dropping out otherwise. That's what it's still predictive for people who identify in college as being interested in STEM, but less so, because they already have, if you start in college, you're likely to stick with it. A lot of people drop out, the converse of this line would be the dropout rate. This is persistence. But you can see it's consistent with the claim that spatial ability matters early on. Okay. So what we have then is sort of a catch-22 of low spatial skills. If they could get to the point that the semantic ability matters and is available, then their low spatial ability wouldn't matter. If we go back to Zach Hambrick's study of the geologist, he showed that. But they can't get there because of the demands of spatial ability early on. So if we can help them over this hump, if you will, get them through the bottleneck, whatever metaphor you want to use, we can make a big difference. But before I show you that, let me talk to you about STEM joining very briefly. Because STEM joining is very, very important and very, very unaddressed. Okay, so the metaphor we have for not having enough STEM workers is this leaky pipeline. And this is very kind of a George Lakoff thing, that the metaphor that we have is really constrained and influenced how we think about the problem. So the leaky pipeline metaphor says we start with people who are interested in STEM, and fewer and fewer and fewer people go on. So it's like a leaky pipeline. There's a supply, but it leaks out, and therefore there's very few STEM graduates. Okay. This in some ways is a very undevelopmental model, because you've got to know early on, and you've got to stick with it, and if you don't, you're lost, and it's all one way, and it's all one way bad, out. But developmentally, if you've talked to any 20-year-olds, they're rarely that sort of fixed in their opinion. There's plenty of switching both ways. There's switching into and out of STEM majors. It happens both ways. But very few people come in from, it's a 2-to-1 ratio of leaving STEM to coming in, okay? I mean, there's a lot of major switching, but there's less from, for example, psychology into engineering than the other direction. However, there is some, and that some could make a big difference, and that's my next point. So this is from the National Longitudinal Study of Freshmen. It included 28 of my nation's most selective research universities and top liberal arts colleges. And they looked at the STEM majors, what they identified when they were freshmen and where they ended up. So the majority, not quite most, started at, they knew they were STEM and they stuck with it. But importantly, there's 2 other colors here. 23% joined STEM from undecided, and 18% joined STEM from a non-STEM field. These are the people that we tend to think don't exist, the ones who go from psychology to chemistry. They do exist. Now, 18% is a small number, but when we're looking at coming up with 100,000 more STEM majors, which Obama has said we need, then this could really matter. So David did an analysis that we estimated if there were a 5% increase in STEM joining, then we could get to 63,000 more STEM graduates. 5% is a modest number. We think it's doable, actionable, and obviously if it were more, it would be more. But 63,000 is almost 2/3 of what Obama called for, that we need 100,000 more graduates per year. So don't ignore STEM joining, and don't focus only on the leaky pipeline. It should be more like an osmotic membrane where you can go both ways, and people do. Now, how's that relevant to the topic of today? STEM joining is also predicted by spatial skills. And when I say these things, we're holding constant not only math and verbal, as Lubinsky et al. Have done, but also as many other covariates as we can possibly think of. Several things I'll talk about in a second. So this relationship is as real as we can get in a non-experimental context. Okay, so there's something you can do about it. And by the way, if you're interested in equity for women, there is less STEM joining by women, but this is a particular point of leverage where if we get more women to join into STEM, we can make a much bigger difference than we could by getting them when they're in 8th grade and making sure they don't drop out. There's a huge untapped human capital resource here that we're not exploiting, and part of the reason is spatial skill again. One other predictor is the number of STEM classes they take early on. This is sort of a natural experiment. Across these 28 top institutions, there's tremendous variation in the distribution requirements. So all freshmen are required to take before they graduate, some science and mathematics. That's just about universally true. Colleges vary dramatically on when they have to do that. So I can't name names because of ethics, but some colleges require 2 STEM classes in the first year. Northwestern is not one of those. They do require 2 STEM classes, but not necessarily in the first year. This turns out to be critical to the process of STEM joining. We've looked at it in 2 ways here. The percent of first-year credits earned in STEM. Okay. These are amongst people who did not identify as STEM majors coming in. So these are STEM joiners. And basically what these 2 curves are saying is to become a STEM joiner, STEM experience is absolutely critical. So you've got some people who say, I don't think I like chemistry, but I'll give it a try. And giving it a try at least twice, 2 different STEM classes in the freshman year is an absolutely critical, nonlinear influence. So again, if we get that person who's willing to take a STEM class or is forced to by the curriculum and help him or her succeed to get to the necessary 2 or 3 early on and succeed in those 2 or 3, then we have a real chance of STEM joining. So, and I haven't shown you the curves for spatial ability, but they look very similar to the obverse, whatever, of the STEM dropout. Okay. Now, I have implied that spatial cognition doesn't matter for expert performance, and obviously that's not true. Why have we persisted with that belief, though? When does it matter? And I think for great insights, like finding the structure of the DNA molecule, or realizing, as Rosemary, did I say? She was the one who initially came up with the idea that the 2-dimensional X-rays could provide inference into the 3-dimensional structure. Watson and Crick then stole that and made it got the discovery of the actual properties, and she never got the full credit that she deserved for the inference that you could make a 3-dimensional structure from 2-dimensional X-rays. So this is the truly exceptional scientists, the one that sort of break out of the semantic knowledge and have insights, may in fact be spatially gifted. I've for many years started my papers off with this example, but we don't need everybody to be Watson and Crick. What we need is more people to get through organic chemistry, and preferably to do so early in their college career. And by focusing on Watson and Crick and their high spatial reasoning, we actually may be doing a disservice. Because average spatial ability is good enough, perhaps with a little bit of help, which is what I turn to now. I'm going to talk about 2 different approaches that we've worked on. One is a meta-analysis of what are largely, but not completely, lab studies of spatial training. So the question that we addressed in this meta-analysis is, how much can spatial ability be improved through training, some cases life experience? The second approach is a much more sort of contextually relevant approach, where we are trying to not only improve spatial skill, but make students spatial thinkers. And the reason I think both approaches are important, there is a legitimate debate that sort of like mind is muscle doesn't work, that just the first approach to train them will make them good at mental rotation, maybe, but doesn't really transfer to STEM. And I should say there's some research coming out that suggests that it might transfer. And in this case, the mind is muscle thing might work a little bit, because spatial ability is so undertrained that even a little bit of transfer might be enough. So I've heard the mind is muscle thing. I'm very aware of that. And I know there's a question about transfer. But in this particular case, a little bit might be enough. But nevertheless, I realize I don't expect, just by putting somebody in front of a computer screen for several hours, that I'm going to turn them into Watson and Crick. And so I do believe that spatial thinking, spatial visualization is something that needs to be embedded within the entire curriculum. So to the extent that there's time, I'll talk about both. Okay, so this is the meta-analysis of spatial training, and there's many, many kinds of spatial training. Some is based on video games, a lot are based on laboratory studies. Nora has done quite a few of those, one of the few to train to asymptote, which is no fun at all. And because people have so little experience, it takes a long time for them to get as far as they can possibly go. But Nora, to her credit with her colleagues, got both men and women there. In a few cases, it's taking STEM courses. So it's the opposite question. How does taking a geology class affect your spatial ability? And in one paper, there was a dress design where there actually is arrangement of parts, and it doesn't scale up exactly proportional. So when you go from a size 4 to a size 8, it's not the case that you just double everything. So there's some reasoning that goes on there. Okay, so the meta-analysis included 217 studies, of which 54% were unpublished. And I'm just going to go through the results very quickly to make sure I get to the second part. The results can be summarized very succinctly. Training works, training lasts, and training transfers. Median effect size, and this is quite conservative because the control groups tended to improve too, but not as much as the training goes. So this is with full control. Most, but not all studies included controls. And so this is accounting for all the things like test, retest, and all that. I mean, even above and beyond that, there was a median effect size of 0.43, which is almost half a standard deviation and a moderate improvement. And as I'll show you in just a minute, you know, it's not a huge effect, but it's not a small effect, but it could make an enormous difference. You know, just to give you some context, the effect size for taking aspirin to prevent heart attacks is less than 0.1. You save maybe 3 out of 1,000 people who do it. But over the course of several years, over a population of several million, 100 million, we saved a whole lot of lives with a very cheap intervention. So the small effect size can make a big difference because economically those are often the cheapest ones. And we're talking about millions of students here. So this is not that small. It's equivalent to about 7 IQ points. Now, training lasts. Okay. Now here we start getting into a problem of self-selection of studies. This is necessarily retrospective. I can't go back as much as I would like to. I can't change the designs of the studies. So when I say training lasts and training transfers, let me just say right up front that this is limited to those studies that actually train for that. So if you know you're going to go for a delay of, in some cases, several weeks, perhaps the training was more intensive. Or no, I know it was more intensive. So we've knocked out about 75% of the studies when we start to look at those that go beyond even a day. So most psychology studies last an hour at most, and they will show an improvement over that hour. That's not educationally relevant, but several weeks might be. Amongst those studies that did include substantial delay, they actually found no decrement. And I know that violates everything all the way back to Ebbinghaus and all that, but again, it's probably an issue of self-selection. So, but it is existence proof that you can get training to last. And the same with transfer. Does the task affect performance on other things that weren't trained? And this is also a common criticism of training studies is, okay, so you train them to do mental rotation with these particular figures under these particular circumstances, but there's a huge amount of literature that shows that that doesn't transfer, and so what good is it to do? And that argument comes up again and again and again, but there were about 25% of the studies, it included at least medium transfer. Now, far transfer would be the sort of holy grail that we're really interested in, which would be like STEM. Medium transfer is going to a very different spatial task. And near transfer would be like a different form of mental rotation or something like that. And so once again, we find that there's no effective transfer. In other words, you're just as good on a transfer task as you are on the train task for those studies that included it. So I'm trying to be conservative here. I think the situation is actually better than what I'm saying, because if we were going to implement this, we wouldn't have to go with the average one. We have plenty that we know are a lot better than 0.43. So if I put on a policy hat, I wouldn't use the average. I could do something much more effective than that. Okay, but let's go with the 0.43. So what? How much difference could it make? Okay, well, again, relying on Lubinsky and colleagues, we were able to look at, going all the way back to that second slide, look at the average difference of engineers' spatial skill from the average population, and then say, okay, what if we increase the average population by 0.43? And what it turns out is that you could double the number of people If you believe that spatial ability is a limiting factor or makes people drop out, and that the average level of the average engineer in spatial ability is sort of a necessary place to get, that makes you spatially qualified, if you will, we could double the number of people who meet that requirement with a 0.43. How much time is okay? That's about right. Okay. Okay. Now, as I mentioned, there is some work showing that this works for STEM, and that is sort of the raison d'etre of Silk, if you will, is that spatial ability improvements could lead to STEM improvements. And those have been demonstrated for the most part in sort of local places like measurement or something like that. Cheryl Sorby at Michigan Tech and now Ohio State has a comprehensive training program that's specifically designed to reduce dropout amongst engineers, and she's at a sort of mid-level engineering school. So they recruit a lot of people to Michigan Tech who would struggle in engineering, even though they've decided to be engineers. This is the exact group we want to focus on. We want to try to prevent dropout. And this a very interesting sort of experiment of nature or regression discontinuity design happened when the course went from being optional, this spatial training course, to being required. And what this graph is showing, so if we look at the relation between mental rotation score on the x-axis and calculus grade, there is, across the entire group, a correlation. As one goes up, the other goes up. Okay, but when they required the course, we get this regression discontinuity, and it shifts the distribution upward, and that is this is the next best thing to a true experiment. Several methodologists have argued that this design is arguably as good as a true experiment because they don't differ in any other way, and they only differ in time by 1 year, so it's unlikely to be a cohort effect. And it improves calculus, which is quite a bit of far transfer. One of the things we're trying to do now is understand what elements of calculus does it improve by looking across a online class. I think I'm just about right. Okay, now my final thing is to talk about the broader contextually based approach. This is coming at it from more of a science education point of view. And the next generation science standards, which are quite controversial and not adopted by anywhere near the majority of the states yet. This is not Common Core. This is a science which is not addressed in Common Core, but the sort of analog to that is this next generation science standards. Again, several people at Vanderbilt have been very active in that as well. And the goal of these standards is to treat science as practice, that to get away from just memorizing facts and to emphasize science as practice and broad domain general skills such as modeling and evidence-based reasoning. And the theory is that if you practice this in different domains, it's much more likely to be applied to new ones. Basically, we're training people to be scientists rather than just memorizing a lot of facts. And so with Bob Colvert, we've been emphasizing a spatial approach to these practices. Can we make people spatial thinkers? And this is characterized not just by mental rotation, but it also includes like metacognitive awareness that there might be spatial solutions. When you see a new scientific problem, do you think about the possibility of a spatial solution to that? These are real-world tough problems, like, for example, if you were going to locate some wind farms off the east coast of the United States, where would you put them? Okay? These are the kind of questions that students are going to face, and they're often going to be about spatial distributions, because you've got all kinds of problems you've got to solve. Bird flight, ships, proximity to electrical networks, all these things become, and wind patterns, all these things become important. Importantly, they're better solved through spatial distribution. So what Bob has done is create a course called the Geospatial Semester. In some cases, in many cases, actually a geospatial year. This is an advanced elective, so for now it's limited to only those students who have already reached senior level and taken at least 2 prior science classes. So many of the same students would take AP Physics, but instead of that, they may elect to do this. And it's marketed in part by relevance to many different careers. GIS sciences, geospatial science, is one of the top careers in demand. Okay, and so what the geospatial semester is a dual enrollment partnership with his University James Madison in Virginia, and the students can get college credit for it. And it emphasizes, the first part of it is technical, learning to use relatively easy versions of ArcGIS. GIS is a program that allows you to layer different kinds of spatial information. And these numbers just only increase. So the first focus is GIS use. And what GIS does is allow you to think about distributions and patterns and lay them and see relations as they emerge organically by laying them on top of one another. So here, if we're, for example, a marketer or a real estate agent or interested in flood prevention or whatever it might be, we can look at the spatial distributions of different relevant information, how the land is used, how the customers are distributed, and put those together and find patterns. And that's what we mean by spatial solution. Okay, here's one example of the kind of final project. Both of these are from the rural high school that's included. This girl was the daughter of milk farmers, and she started with a very simple question. Where does our milk that comes out of the cows on my farm, where does it end up? Turns out the answer to that is all over the world. But that simple question prompted a lot of problem finding and learning about distribution routes, about the fact that once it gets to ports, it's made into powder and then shipped all over the world, and income distribution. She also even faced some ethical concerns about asking people how much milk they produce, because that was paramount to asking their income. So she went through this process of thinking through the problem. Here's another one, again emphasizing the local nature of it. This is, the problem here is bears come in from the Shenandoah National Park and they want to take them out and release them back into a safe area, but you've got these constraints. You've got to have a car or truck that's big enough to accommodate a bear and yet can go through the Forest Service roads. So this student figured out the best areas within Shenandoah Park where they could put the bears with the least probability of them getting back. So we've been studying the effects of the geospatial semester on students' reasoning and thinking, not just spatial ability. Using a variety of methods, qualitative as well as quantitative, which is their final project score. And I'll tell you about this. I think I have time to do the spatial word counting. This is the very crudest form of discourse analysis. We're just counting the words that they say, the spatial words, but it tends to reveal a lot. Okay, so we asked them questions at several points across the school year that could be solved using a spatial approach, but need not necessarily be. So if you were running a campaign for local political office, how would you go about running your campaign? That doesn't necessarily sound like a spatial question, but look at one of the answers to it. Cross your fingers on this. Okay. Well, okay. Well, you can't hear him. Watch him gesture like crazy. I do have his words in a second. Okay, so he gestures a whole lot. And here's what he said. First, I would use probably something GIS related to find an area that would probably maybe suit like my platform. Say like I was maybe for gay marriage, for example. So I do like a map and I have like a poll. I can find like data on who supports it or not. And then plotting it like on a map, I could see who supports it and then maybe campaign there. So he's obviously thought about this as a spatial problem. And we can, he also has done a lot of the scientific practices that are emphasized, like constructing explanations and analyzing and interpreting data. Now, if you watch this other girl who was in the comparison group, which are AP Physics and History students, you will see no gesture at all. And I don't have her transcript, but she just says, I would buy up mailing lists and things like that. Okay. Okay. So analysis is based on a very simple assumption that the words people use reflect what they are thinking about. It started with clinical psychology on happiness and sadness, but it's grown tremendously. And so the critical question here is what dictionary to use. Pennebaker included a spatial dictionary, but we modified it based on some silk work. This just shows you the pattern over from the beginning to the end. These are just spatial words, but unique spatial words. We only count each word once. So it's not like saying right, 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 right. It's a unique spatial word, which we are taking as a proxy measure of spatial thinking. The AP comparison actually goes down. I don't know why that happened. Maybe they burnt out or something like that. But the important finding is here that there's a tremendous advantage of spatial word use. And as I said, I'm running out of time, but there's many other measures that converge to show that really this can make a difference not only in what they know, but how they approach problems. So the final message is that spatial ability matters for STEM, but perhaps not for the reasons that are typically assumed. It matters for preventing dropout and for permitting entree. Spatial ability is malleable, and the cognitive component is probably important, but if we really want to make students spatial thinkers, we're probably going to do more than that. But if that's all you can do, it's worthwhile. Okay, I think I finished in time. I'm between you and your dinner.
Right, but I'm sure somebody has a question here. Questions?
Actually, I really enjoyed this talk because I've heard fragments of this research, but it's really great to see it all in one place, or at least most of it in one place. So I'm of course, really interested in your idea that I've heard before that from you, that the use of spatial words, number one, the use of spatial words will be a decent barometer of spatial thinking, and two, that training in that the kind of training you're doing in the geospatial semester will increase their sort of spatial vocabulary. How direct do you think the connection is between the kinds of words they're going to be sort of using of necessity during the course? I mean, have you checked that? That is, if their spatial terms increase, are those the same terms they've been using or been exposed to, or?
GIS in the dictionary. You don't get credit for saying GIS. Second, remember, it's the variety of words. So you only those bars only go up if you use a new spatial word. So in addition, I didn't have this data. I don't know if this actually answers your question, but in terms of validating this as a measure, we do have correlations amongst all the other measures, and they are in the 0.4, 0.5 range, which is not horrible. I'd like them to be higher. I think my claim is it's tapping a more general approach to problem solving. And one more bit of evidence for that. You can't just do this out of context. I mean, you have to have some context, and we do analysis of, for 25% of the students, we went a certain amount before and after we did the word count, just to sort of see, are they talking about what we think they're talking about? I mean, the extreme example would be, you say, you're right, that count as a spatial word, and if we did it multiple times, which we don't, we could inflate it. And so we want to be careful. And the scenarios, we only found like about 3% of the time where it was actually not what the crude analysis would reveal. But as a natural language analysis, this is really, really low level. Nevertheless, it's proved really powerful in clinical work with Pennebaker, and it can be one of several ways you need converging evidence, but I think it does converge.
Okay, and Alex had a question.
Oh.
Just for clarification, I'm not quite sure that I fully understood what is meant by STEM joining.
STEM joining means becoming a STEM major even though you did not declare as one. Universities vary so much in what they expect or require of their freshmen. That's such a fascinating analysis on its own. I believe Ken correctly, if you want to be an engineer at Northwestern, most of them apply to that school. Is that correct? So that would be the most difficult way to join STEM. But it could also be if you're a student in a College of Arts and Science and you come in and you say, I'm undecided, or I'm a psychology major, which for this analysis I am not counting as STEM, you could fairly easily become a chemistry major. So it's leaving either the undecided category or a non-STEM major and becoming a STEM major. And we have data on graduation. I don't think there's any data yet. This study's pretty young on post-graduation attainment. I will say, it's like if you're interested in the experience of freshmen, it's a fascinating. I didn't talk about hardly any. It's just a fascinating study of how curriculum could have an influence on what students take. It's really interesting.
So I thought your talk was great. I love this work.
But.
Yeah, the but is that there have been recent reports that we have more than enough STEM graduates.
Oh, don't do that.
That will fill all the STEM jobs plus some. So I'm wondering if you would like to comment on those claims. I know nothing about this except what I've read.
It's a topic of great debate. One answer to that is whether they're American or not. So if you will hire people who are willing to accept lower wages but are STEM experts, then we have a source of human capital for STEM. If you believe it is important for American students to be good at STEM, then we don't. So this gets into economics and hiring off seas and all that stuff. So they do have a way of fulfilling the need for STEM workers. I mean, that's a very important. Let's just say you wanted to increase the percentage of STEM workers, which the president happened to say as recently as 2012. So.
I mean, would it be
Could the president be wrong?
I mean, I'm sympathetic with your motivations, but wouldn't it be just sufficient to say that the average starting salary for a STEM graduate is about $15,000 to $20,000 higher from a general liberal arts graduate?
Sure. That takes it away from being this sort of passionate national problem that we have to address.
Okay, that's true.
I really have to.
Oh, I'm not using this as an argument against the enterprise at all.
No, you're absolutely.
Yeah.
I mean that.
Okay.
The way that many STEM industries fulfill the human capital need is by going overseas. And there's big some have argued that we should cut down the number of H-1B visas. Some have argued that we should increase the number of H-1B. So this is desperate need. It'll take 10 years to fulfill with Americans, so we have to keep hiring from overseas. It's economic exploitation. Okay.
So David, I have a question that's not about STEM.
Okay.
Is Go more like chess or like Scrabble?
That's a great question. I don't know that much about Go. This could be the real intermediate example. I don't know. Does anyone know? Do we have a Go expert? It's a Japanese game.
One person who studied Go basically says that anyone who's really a champion never reads at an adult level because they've invested so much time that they don't ever really learn to read terribly well.
It's a great question.
So I really enjoyed your talk also, and I'm a big fan of promoting spatial thinking and spatial practices and so forth. And then I've got a bot like Tim. But as you were talking, I thought to myself, a lot of the elements that you're talking about are not particular to space at all. And so I don't know whether you've ever thought about doing the control studies are, the kinds of critical analyses that you're talking about, posing questions and coming up with coherent answers and et cetera, et cetera. You can go down, I was going down the list, and any literature course or history. And so actually I wonder whether the improvements that you have, although you're testing spatial, and sometimes you find, I guess it doesn't extend to verbal, but you could get the same, if these are really much more general skills that you're promoting, it would actually be extremely powerful. It might not be so good for a center that focuses on space, but actually, that might be okay. So I'm curious to know what you think of the relationship.
That is called the Brian Reiser question. He's a colleague of mine in learning sciences, and he basically said, isn't this just good instruction and good learning? What's spatial about it? Which, he asked my second-year student as she was doing her master's presentation. That was a really good question. There are many approaches to trying to promote critical thinking and analysis. This one does come with the technologies that are necessary, and they're not that easy to learn. So some of it's absolutely critical to be taught. I guess I would say that if we are having a more general effect, which I don't think we are, and I'll tell you about why I think we do, then I'd be happy. But I think that the problems, let's put it this way, GIS has opened up a new way of thinking. It has had a transformative effect on spatial problem solving. Teaching those skills, I do think, pushes you a little bit more towards spatial analysis, or critical thinking is going to be spatial thinking, is another way of putting it. So there we can have our cake and eat it too. Now, a little tiny bit of data that shows it's not as general. Luke has 42 some different categories, and the spatial goes up tremendously. Others, most aren't affected at all, whether those are getting to critical. He does have a critical thinking scale. It's not very good. I mean, you know, if you're skeptical about whether you can get spatial reasoning out of people's words, then critical thinking, you know, we may have to use something like LS&A or, oh my God, human coding, which is really hard and slow. But I do think you could get it there, and to the extent that we have been able to measure it, we did not find an effect. And I don't know whether that's good or bad. But so I'm really dealing, you know, like my first answer to you is great, but then as the experimental psychologist, like, no, it can't be, it has to be more specific. I think I'll go with the great.
Okay, well, why don't we have just one more question, and then
it should be just a quick follow-up. It seems to me like the STEM as a natural class is really sort of politically or economically aggregated. And also, what little I know about some of these subjects, it seems like there can be within discipline variation. So for instance, a mathematician looking at topography versus, or well, just the canonical difference between algebra and geometry. So in relation to Barbara's question, have you looked at differences within fields with respect to how heavily they rely on spatial stuff?
The straightforward answer, if you just want to go to dinner, is no. I can give you some, there is some other research. It needs to be qualitative because you're talking about really subtle differences. To the kind of analysis that we did, you know, it's starting with 100,000 in 6th to 8th grade, and we're ending up with like less than 100 in each of those cells. So to get within that would not be possible within this data set. I do think this is a call for, you know, these kinds of longitudinal studies, which under current IRB rules could not be done. So just look at how much we're learning, and this study couldn't have been done because they didn't know that they were going to be asking them for follow-up, and so they couldn't have followed them up now. So make sure you get permission to follow up people, and you know, think about what we're losing. Didn't think I would end there, but it always comes up.
Thanks.
You're welcome. And thank you to Daisy for helping.
Thank you. It was our last presentation at this conference, and let me thank you all for the wonderful conference. Thanks to speakers, thanks to chairs, and to all participants. And I'd also like to thank my co-organizers and friends Mark Glansberg from Northwestern and Peter Svenonius from Tromsø, who are not present, unfortunately, but they are virtually in thoughts with us. So, and I would like to thank our helpers and our local organizing team, Christine, Ande, Lieve, Britze, Marta Selecka, Marta Bancevic, Dacu, Notiņa, Andrejs, Vojevoda, Jānis Pencis, Signe Mežinska, Chris Leškevica, and Lieve Reiter. So thanks a lot for and of course, thanks also to the University of Latvia for supporting us, and also for the Department of Computer Sciences, who kindly provide us with rooms for parallel sessions yesterday. And I think I'm definitely forgetting somebody to thank. But yeah, well, that's in terms of acknowledgements. All I wanted to say, there are a couple of practical issues. Practical issues. First of all, there is actually the idea that we could put some of or all of presentations on the conference side. So if you like this idea, please send me your presentations. I'll upload on our conference side. So the second practical issue, as you know, we will have also a publication of conference papers in the Baltic Yearbook of Cognitive Science. So we will send you a circular. In terms of deadlines, we will. The first deadline will be at the end of year, so you will have a couple of months to think about modifications and kind of updates. So anyway, I will send you a circular concerning practical issues and timetable. So then there are two announcements concerning tonight. If some of you need a certificate for confirming that you have attended this conference, so please go to Christina, who will kindly provide you with this kind of official confirmation. So, and the last thing I want to say, we have a conference dinner tonight, so at 7 p.m. at restaurant Neighborhoods. So we will be 6:45 at Hotel Neighborhoods, and those of you who are at Hotel Neighborhoods, you could go together to the place where our conference dinner will take place. So that's not far away, but so 6:45 at the Hotel Convent, and then we will go further to restaurant. Okay, so that's all I want to say, and again, thanks a lot, and I hope to see you sometime in Riga again. It was really amazing conference and amazing talks. Thanks a lot.